Okay, welcome back to the Mentored Engineer. In this episode, we are going to take what we learned last time is the calculations for the vertical tube on the jib and put them into MathCAD and calculate our stress. So let's get started. Okay, so you can see here in MathCAD that we've got a new header, vertical jib tube calculations, and we've got our picture from what we drew on the whiteboard earlier. So let's go ahead and specify or recall the variables that we've used before just to make sure that they are still current. So our weight is 1,000 pounds force. Our length is, let's see, 4.5 feet. Our D3 is equal to 2.83 feet, which is 34 inches. All right, so I think that's all that we brought in. So let's look at, we need our theta, which is 5 degrees. All right, our mu, which we said is the this is the coefficient of friction. That's 0.5, and that's unitless. All right, we've got D1, and that is 4 inches. And our height, which is about 6 inches more than D3. So let's put that at an even 40 inches. Wonderful. Okay, so it looks like we have everything we need to calculate the moment. So let's go ahead and do that. And that's the weight times, I'm just looking at the picture above here, the length plus, plus the height times the sine of our angle plus D1. And we said in the previous video that we would not use the cosine because it's 0.996, which is almost 1. So we're just not going to go through that. Oh, forgot our closing brackets here. Okay, there we go, no errors. And we're going to calculate our moment arm, which do in inch pounds. And that is quite a bit. All right, so now we're going to look at our torque. And actually, before we do that, we need to calculate the force on the torque, because that's the next thing. It's going to be the weight times length plus D1. Once again, no account for the cosine there. All divided by D3. All right, and we'll find out what that is equal to. In pounds force. Okay, 1,700 pounds force. So let's look at our torque, and that's going to be equal to mu times the torsional force times the OD divided by 2 times 2. And let's find out how many inch pounds that is. All right, so that's 4,000 inch pounds. That's not many. Okay, so let's now, we got to put in some stuff about our section. So actually our OD here is wrong because we haven't specified that yet, but it'll correct in just a second here. So I think that is a 5-inch tube with a 4.5 inch wall, or 4.5 inch ID. All right, so our torque should change a little bit here unless our OD up here was the same. Almost the same. All right, cool. All right, let's get rid of that. Okay. We'll bring that down. Okay, so we got our torque, we got our moment. Now we're going to need our area of the cross section, and that is going to be equal to pi over 4 times the OD squared minus the ID squared. And I always like to work in terms of the diameter, and that is simply because you can't measure a radius. You can measure the diameter very easy with a tape measure, calipers, whatever, but you got it there. You don't have to convert it and then convert it back. Unfortunately, all of our formulas that we learned and memorized over the years are in the radius. So pi r squared, yes, we know that. The other one would be the area moment of inertia, which is pi over 4 r to the 4th. It's a nice form. It's easy to remember, but doesn't really help us. So let's go ahead and calculate what the area is. Alright, so the next thing we're going to need is our section modulus. Alright, and I have done the work of figuring this out. It's kind of a unique formula as far as what you would think it would be. But it is mathematically the same as subtracting the two areas of the area moment of inertia and then dividing that by c. And it's simply, pi over 32 times OD to the 4th minus ID to the 4th divided by OD. And I encourage you to figure that out for yourself and make it your own. Make it something that you trust. Don't just listen to me because I'm telling you what it is on a video, but prove it to yourself. I've done it. I actually developed it, so I had to make sure it was right, and I would just go into MathCAD with a bunch of different units, and I thought it was by algebra, and then just figured it out for myself. All right, so the next thing is I've never seen a real unit or a variable descriptor for this. If you got one, please let me know. I call it S sub j, and that's the torsional section modulus. We use I for an area moment of inertia and j for a polar moment of inertia, so that's why I just put the subscript j. But as far as I know, there is no official variable, so I've just used that and grown accustomed to it. So hey, if you want to use it, great. If I see it on the calculation someday, I'm going to be like, hey, it's exciting. All right, so let's calculate our normal stress now. As soon as I find my mouse. There it is. Okay. So our normal stress is going to be the moment divided by the section modulus plus the little force that we have is going to be a very small component over the area, and it's going to be equal to almost nothing. Oh, actually, this will be the primary driver. 14,718 psi. All right, so that's pretty good. We also forgot to specify a yield strength, which for hot rolled material, it's 32 ksi, I believe, just generic one. If they specified something else, I wouldn't know about it, so we'll see how that goes with this. All right, and then our torsion, or shear stress, is going to be equal to torque divided by S sub j. All right. And that is equal to 1,000 psi. And that's about what I expected. There's not much there. It's mostly the moment that's doing the damage, and you can see that's almost 15 times as much. All right, so the last thing to do here is go up in our calculations and find where we use Mohr circle. I highly suggest, if you haven't seen it yet, look at the Mohr circle video and figure out where all this comes from. And you can see, wow, we got a little problem here. I always love to have a design factor of 3, especially on things where I don't know what they're made of and don't know what they're necessarily doing. Have the safety factor of 3. And you can see here our safety factor is 2.16. So either we need to go back and look at using a bigger tube, maybe taking a material sample of the tube, or just do a hardness test on a non-critical part, and that can give you a better idea of what the yield strength actually is. So in this case, 32 ksi is rather low. But if we moved it up to 40 ksi, or if it was a DOM tubing of, I believe 60 ksi is 1020 DOM, or you can get up to 72 with a 1026 DOM tubing. So you can look in there. I think we'll just keep it there for now. So there's a couple of takeaways here. The first is we don't know the material, so we could do a hardness test to find that out. Another one is just knowing that this has already been in existence. Maybe a 2.16 design factor is okay for what happens. Do we load it up that much? Maybe do a sample. We should also look at the straightness of the tube. Has it bent? If it's bent, then we know it's even higher than this. So there's a lot of things that go into it. Don't just say it's a bad design when clearly it hasn't bent in years and years of being used. I mean, this thing is almost 30 years old, and structurally it hasn't been changed. So it's got a lot of fatigue cycles on there and a lot of time in the field. So maybe we are overly conservative here. But always err on the side of caution and make sure that you have somebody check your work in case you did make a mistake. All right, well, thank you for watching this episode of The Mentored Engineer. Thank you for spending the time to watch it, and please stay tuned for our next video. Have a great day.